In this video, we're going to begin our discussion on graphs of rational functions. And we're going to break this into probably 3 different lessons if everything goes as planned. So we're going to start off with some exploration, and then we'll move into sort of the more quick the analysis version of how we'll do this. This is all review. You have learned these concepts in the past. But they may, kind of as a one-off chapter, and we didn't revisit it very much. So you may be a little bit rusty on this. So we're going to just take it from the top, but we're going to go at hopefully a pretty good pace. All right, so graphs of rational functions. We just talked about rational zeros a couple sections ago, and a rational zero, or rational anything, is talking about something that can be written as a fraction. So today we're talking about rational functions take the form of P over Q, but P and Q are themselves polynomial functions. So we're still kind of dealing with polynomial functions, but now we're dividing these polynomial functions. And then you'll notice there's this little qualifier here that says Q of X cannot equal 0. And I hope that is kind of obvious at this point in the year. We cannot divide by 0. So anything that causes Q of X to be 0 is a problem for our domain. All right, so what I'd like to start with, and I'd like you to play along and do this in your notes, is we're going to do an investigation. So I want you to fully investigate 1 over x. Now, I'm going to do some of these by hand. I'm going to start in the middle here. 1 over 0 is undefined, so I don't have an answer there. 1 over 1 is 1. 1 over 2 is a half, is a third, is an eighth, is a tenth, is 1 over 6 million, right? Now, if I turn these into decimals, just so I can kind of see what's happening, this is 1, this is 0.5, this is 0.3 repeating, this is, I should know my eighths by now, but you know what? I just don't. I want to say it's like, I know it's point something 0. Anyway, I don't know what it is. Let's just find out. So I'm grabbing my calculator. Actually, I'm going to use my screen calculator here. And so 1 divided by 8, 0.125, 0.1. And I've jumped from 10 to 6 billion or 6 million just to give you an indication that if I want to know what something looks like, I just keep exploring. So maybe I don't do 6 million next, and maybe I do 1,000 next. But if I did 1,000, right, that's 0.00 tens, hundreds, 0.001. And if I do 1 over 6, and I'm sure my calculator is just going to say, hey, dummy, let's use scientific notation. 1, 2, 3, 4, 5, 6 zeros. It gives me 0.0000 6 zeros. 1, 2, 3, 4, 5, 6 zeros. 1666. Okay, so what is the takeaway here? If I start graphing these points, I've got 1, 1. I've got at 2, a half, a third, a fourth, a fifth, a sixth, an eighth, right? That's 1, 2, 3, 4, 5, 6, 7, 8. I don't know how to graph 0.125. It's just going to be like right there. I get out to 10. I've got 1/10. I get out to 6 million. And if I'm going to graph 0.00001666 on my graph, it's going to look a lot like I graphed the last point. In other words, these values are getting very close to 0. So if I just take what I have done so far, there's an indication here that I'm getting closer to an output of 0, but I'm not actually getting to 0. And if I keep getting bigger and bigger numbers, I'm just going to get closer and closer to 0, because a small number divided by a very large number is basically 0. I plug in -1, and I get -1. -2, I get -a half. -5, I get -1/5. -1/10. -1 over 2,000, which of course is -1, negative 0.5, negative 0.2, negative 0.1, negative 0.002. Okay. And so once again, if I plug these values, or I plot these values, I did 1, 2, 3, 4, 5 is 0.2, 6, 7, 8, 9, 10 is negative 1/10. And then closer I go, or the further I go, the closer I get to 0. And so once again, it looks like I'm approaching 0, this time from underneath, and then, but never quite getting there. Okay, we said there was no value at 0, but I also haven't explored the entire graph. And so here I've said, what do we need? What do we need more investigation on? So let's figure out what's going on between 0 and 1. So I think I'm going to do 1/2. So then this is just 1 over 1/2, which is multiplied by the reciprocal. That's just 2. So at 1/2, I'm at 2. If I do 1/3, I'm 1 over 1/3. That's just 3. So 1/3, I'm at 3. At 1/4, I'm going to be at 4. At 1/10, so microscopically close, I'm at 10. If I graph 1 over, so let's just write that down, 1 over 10 is going to be 10. 1 over 100 is 100. 1 over 1,000 is going to be 1,000. I can't ever plug in 0, so as I plug in 0, the whole thing goes away. But as I get microscopically close to 0, what seems to be happening is that my graph just keeps getting bigger and bigger and bigger. And so I graph that. Plugging in negative versions of the same thing is going to lead to the same result. And I'm going to get something that looks like this. All right. So let's take a look at what I've asked you to do. Fully investigate 1 over x. All right. So what have we learned here? We have learned, if I was going to summarize, I would say that we have what's known as a horizontal asymptote at the axis. There's a horizontal asymptote, the equation of which is the line y equals 0. I have a vertical asymptote right here at the axis, and this is the equation of the line x equals 0. So I have, to summarize, I have, looks like no x-intercepts. I have no y-intercepts. I have a horizontal at y equals 0, and I have a vertical asymptote at x equals 0. Let's graph it on our calculator just to see what it shows. And this is not so much to verify it, but I want to just kind of show you the limitations on your calculator. So I'm going to go to Zoom 6. And it shows me this, which doesn't look too bad. I'm just curious. I'm going to go to my format here. I'm going to turn off my axis. Okay, so this is what it's showing me. And I need to be very careful in understanding that there are limitations on my calculator. And it looks like it's stopping there at some value. But as we can see from the numbers and the math, that's not really what's happening. I can't exactly tell you why the calculator isn't doing this correctly or showing it correctly. It just simply has to do with the algorithms that the calculator uses when it's doing calculations that involve infinity. All right, let me turn that back on. All right. So now, would you please do additional investigation here on our next problem? So this time, let's investigate what's going on at 1 over x minus 2. So pause the video, see if you can get the whole thing. And again, you might just know what it looks like based on prior knowledge, but let's go through the motions. Okay, I'm going to plug in 0. This time 0 is not a problem. Plugging in 0 gives me negative 1/2. Plugging in 1 gives me 1 over 1 minus 2. That's negative 1. Plugging in 2 gives me 1 over 0. That one is a problem. Plugging in 3 gives me 1 over 1. Plugging in 4 gives me 1 over 2. Plugging in 8 gives me 1/6. 10 gives me 1/8. And the bigger the x, I'm just taking 2 away from it. And so I'm getting, basically the same results I got before. In fact, it's kind of stupid for me, I think, to take the time to do 6,000 minus 2 and write it down that way, or 6 million. Because, again, think about the difference between 6 million and 2 less than 6 million. It's basically 6 million, right? Like, who cares? Because what's happening is the point is I'm doing 1 divided by very big. Whether that big is 2 off or it doesn't really matter. This is heading to 0. It is not 0. It's getting close to 0. And if I go in the negative direction, I get, let's see, this would be negative 1 makes negative 1/3, negative 1/7, negative 1/12. And again, plugging in 2,000, I mean, whatever. It doesn't really matter that it's 1 over 2002 negative. It's still, again, negative a 1 over big, which is approximately 0. So if we graph these, at 2, I don't have a value. And that means I have a vertical asymptote at 2. Notice at 3, I'm at 1. At 4, I'm a half. 8, 5, 6, 7, 8, I am 1/6. 10, I'm 1/8. And the point, of course, is the closer I get, the closer it gets to 0. And flip it around. At positive 1, I'm negative 1. At 0, I'm negative a half. I'm negative a third, a fourth, a fifth, a sixth, a tenth, approximately 0. Oops, curving too soon. All right, once again, what's going on in between? I think you know the answer. I'm not going to waste a lot of time. Halfway over, I'm going to be at 2. A third of the way off, I'm going to be at 3. A fifth of the way, I'm going to be at 5. A tenth of the way, I'm going to be up at 10. 1/100th, I'm going to be up at 100. And the same thing is happening with the negatives. And so I get this graph right here. What do we know? I have a horizontal asymptote at y equals 0. Label your asymptotes. Oftentimes, if the asymptote is the axis, we don't necessarily put the dotted line because it's just an aid in the graph. And we're kind of demonstrating the same thing with the axis there. So I don't need to necessarily draw on the dotted line. But I do need the dotted line on the vertical asymptote because it has now shifted off of the axis. And it is at x equals 2. Please get in the habit of labeling important points on your graph. I still have no y-intercept. Do I have a horizontal an x-intercept. Knew something seemed weird about what I was trying to say. And in this case, we do, right? We have when x is 0, we got the point 1/2. Plugged in 0, that's how you find a y-intercept. Wow, I did those backwards. Man, let's try that again. The x-intercept is none. The y-intercept is 0, 1/2. Okay, we're back. And we're skipping this part, this do more investigation part. All right, now let's see what's going on this one. Probably going to need our calculator a little bit more here. I'm going to plug in 0, and I get 7 on top and -4. So this is -7/4. I plug in 1, I get 11 and -3. I plug in 2, I get 15 over -2. So -3. Oh, +3, excuse me. 19. Let's scoot over here. I'm running out of room. 19 over -1, so -19. 4, I have 0 in the denominator. I got no answer. 5, I get 27 over +1, so I just get 27. 6, I get 24 plus 7 is 31 over 2. 47 over 6. All right. Keep getting bigger. What's happening? Let's just jump way ahead and go out to 6 million. So that's going to be what? 24 million plus 7? Which probably, whatever math we're about to do, 24 million and 7 and 24 million is probably close enough. But let's just do this. Divided by not 6 million, but almost 6 million, right? What would this be? 5,999,996, which, guys, is almost 24 million over almost 6 million. In fact, I think we could all just sit here and agree, if you get $24 million and then someone has, sorry, here's $7 more, you're like, or hey, come pick up their last $7 tomorrow, you'd be like, you know what? It's not worth my time. I'm good. Same thing. If somebody said, hey, here's $6 million. Oh, crap. Sorry, you owe me $4. You're fine giving up those $4. In other words, with a number like 6 million, we could really just estimate it to be 24 million over 6 million. And 24 million over 6 million is about 4. And if we investigate the other direction, a little typo there with 2 negatives, just ignore that. -2 gives me -8 plus 7. And -8 plus 7 is -1. And over -6, it looks like. Is that right? Just want to think this through for a minute. Do the math again. -8 plus 7 and -6. So this, of course, becomes positive 1/6. -10 becomes -40. Plus 7 is -33 over -14, which, of course, is positive and I put in 2,000 just for fun. I get negative 8,000 plus 7. So that's what? Negative 7,993 over negative 2,004. But once again, negative 7,993 is very close to negative 8,000. And negative 2,004 is very close to negative 2,000. And if I divide those, I get about 4. So let's graph some stuff and see what we know. Let's start at 4. 1, 2, 3, 4. At 4, I have no value. Okay. At 3, I'm at negative 19. So that's just going to be way down here someplace. I'm just going to kind of fake it. At 5, I'm at 27. So that's way up here someplace. I'm just going to fake it. 6, I'm at 31 halves. That's like 15.5. So I'm just going to sort of fake that we're about halfway down. The scale is way off. In fact, we should probably just throw away the coordinate plane and just do this kind of raw. In fact, I'm going to do that because that's just going to get confusing. So let's do this. I'm going to delete that. And I'm just going to start over with my graph. All right, we're going to just mess up the scale. So we know there's a vertical asymptote at 4. Okay, let's try this again. At 5, I'm at 27. So I'm going to just jump up here and call this the point 527. At 6, I'm going to be 31 halves. So that's about 15.5. So we're roughly halfway down from that one. So this is 6, 15.5. At 10, 7, 8, 9, 10, I am at 47.6, which is going to be what? 47 divided by 6 is about 8. So at 10, I'm about 8. And if I keep getting bigger, and I did a pretty big jump, but what did we notice happens? The further we go out, the numbers keep dropping and dropping. In fact, they kind of start cutting in half almost. They're not exactly a half, but they're kind of cutting in half. So the further and further and further I go, we're getting in it closer and closer, apparently, to 4. So what that tells us is we have a horizontal asymptote here at y equals 4. And if I now do the other side, at 3, I'm at negative 19. At 2, right, I'm at negative 7.5 or so. At positive 1, I'm at 11 thirds, which is going to be, at negative 3. At 0, I'm at negative 7 fourths. At negative 2, I've jumped up to positive 1/6. 33 fourteenths is around 2-ish. And by the time I go out to negative 2,000, I'm at a number that is very close to 4, but it's not quite 4. And so I get a graph that appears to be doing something like this. And if I ask what the end behavior is, it is that our graph is behaving just like the line y equals 4. What's all this words I have over here? Let's find out. Oh, I've asked you all the questions. So what is the end behavior? As x goes to negative infinity, what does y do? Well, unlike a polynomial, it doesn't just keep getting bigger. It doesn't keep getting smaller. We saw that it got closer to negative 4. And as x went to the right, we saw that y got closer and closer to 4. Sorry, that should have been positive 4 up here. So we saw that they both go to 4. That tells us that our graph behaves just like the line y equals 4 eventually. Like if we graphed y equals 4 and we graphed this function and we looked at a window of negative a million to, to negative 2 million, what we would see is they look exactly the same thing. What is the domain? All numbers can work except for 4. So my domain are all the x's such that they belong to the group negative infinity to 4 and 4 to, or 4 to infinity. The range. Well, we seem to take on every y value except for that horizontal asymptote. I don't see that we have any value of 4. So it looks like we have all the y's such that negative infinity to 4. Now they're both 4. That's a coincidence. And do we have any x-intercepts? We do have one x-intercept. It is located over here someplace. So how are we going to find an x-intercept? We let the function equal 0. So let's go to our function, which I've lost track of. You know what I'm going to do? I'm going to zoom out here. So I want to know when the function equals 0. So I set the function equal to 0. And I solve it. Now, there's two ways of thinking about this question. The first is we just do it algebraically. And the first thing I would want to do is multiply by x minus 4 to get this out of the denominator. And by doing so, I get the equation. One second. Sorry, this is kind of a little bit messier than I would like. I get 0 equals 4x plus 7. In other words, the answer to this problem is not going to have anything to do with when the denominator does anything. It's all based on when the numerator equals 0. And that should make sense because when you want to know when a fraction equals 0, that's only going to happen when you divide by 0. So when is the numerator 0? I get x equals negative 7 fourths. So the x-intercept is negative 7 fourths, comma 0, which is this point right here, negative 7 fourths, 0. Okay, so what have we learned? Let's back up and take a look at these problems here. In these two problems, the horizontal asymptotes were 0, and the vertical asymptotes were wherever our domain failed us. So why were these problems a horizontal asymptote of 0, right? Why is this one going to 0 while this one went to 4? And what it has to do with is investigating what happens when x gets very large. And so what did we end up seeing right here? When x gets very large, we basically say, you know what, this adding 7 and subtracting 4 just kind of gets in the way. So when you want to analyze this, we can just think about it as f of x is approximately just 4x over x. And when I reduce that, I get 4. Meaning, as x gets very large or very small, the graph acts just like the line y equals 4, because that's what it simplifies down to. On the previous two problems, when x gets very large, this basically, I don't really care about subtracting 2. This basically becomes 1 over x. And then as x gets very large, when I analyze this, I get very close to 0. So it all just has to do with what's going on when x gets very large and thinking about the number sense of it all. All right. Once again, this is not new. Let's go ahead and now think about what we just talked about. On this one, let's call this A. What is the end behavior? As x gets very, very, very large, what happens overall? I get, generally speaking, a small number divided by a very large number. And this one is going to have, as x goes to positive infinity or negative infinity, y is going to go to 0. On this one, as x goes to negative infinity, let's do the left side first. Y is going to go somewhere. And as x goes to positive infinity, y is going to go somewhere. So when I plug in, again, we've kind of had this conversation, but as I plug in 2 billion to the top polynomial, the squared is so much more powerful than the first power, and certainly more powerful than the 7, that when we're talking about the size of numbers that we're talking about, I don't really care about those numbers at all. This just approximately becomes 2x squared. And on the denominator, I plug in numbers like a billion or 10 billion or whatever, then adding $8 or even adding 6 billion doesn't even matter compared to a billion or 10 billion squared. So it really comes down to this. And then what happens to those? You get very close to 2. So as x goes to negative infinity, we're going to get close to 2. And y, we're going to get close to 2. And on this one, once again, adding 3 to a couple billion doesn't matter. Subtracting 9 from a couple billion squared doesn't matter. This simply becomes x over x squared, which is simply 1 over x, which is approximately 0. So how can you summarize the end behavior of rational functions? It all comes down to the degree of the polynomials. So let's summarize what we've seen here. If the degree of the denominator is bigger than the degree of the numerator, then what happens? So the degree of the bottom outgrows the top, so you get small over big. That leads to small over big, which is basically 0. So you have a horizontal asymptote of y equals 0. And if the degrees are the same, then the horizontal asymptote is what? and it is simply going to be the ratio of their leading coefficients. There's a lot of words for a very simple concept. Okay, so notice that's what happened, right? So if we look at part B here, the leading coefficient is 2 and 1, and our asymptote we said was at 2. Here we don't care about the coefficients at all because the bottom is bigger, so it goes to 0. Here we don't care about the coefficients because the bottom is bigger. If we go back and look and see what happened up on this problem, the degrees are the same. They're both linear, right? X to the first power, and the leading coefficients are 4 over 1, and my asymptote was at 4. All right, and we will talk about the scenario where the degree on top is bigger a little bit later. Okay, zeros of the function. So as we talked about, finding the zeros of the function. That was not what I wanted to type. Finding the zeros of the function really comes down to, if you just do the math of it, 0 equals 2 over x squared minus 4 is what I'm asking. And I multiply by x squared minus 4 on both sides, and I get 0 equals 2, which tells us there are no zeros. We asked it, tell us what x value equals 0, and we lost all of our x values. So that tells me there are no zeros. But I already knew that because when is a fraction going to equal 0? Only when the numerator is 0, and 2 cannot equal 0. So we have no zeros. Over here, again, I could take the time and multiply both sides to solve, but this is a huge waste of our time and effort. I don't need to do this because multiplying now both sides by the denominator, I'm left with 0 equals the numerator. So from here on forward, we just need to know, to find the zeros of the function, we just need to focus on the top. And so when is the top going to equal 0? Now we bring in all of our polynomial rules. Now this is a quadratic, but it very well could be a cubic or a quartic. And if you want to know when it's 0, we would run the rational zero test, P over Q, find all of the zeros, and we're fine. Is it a pain? Is there a lot of work to be done sometimes? Yes, but that doesn't mean we don't know how to do it. I'm going to try to factor this and hope for the best. Okay, and I think we're in good shape. So 2x and x, 7 and 1, positive 7, negative 1. That gives me 7x here and negative 2x, which is positive 5x. So my zeros are at x equals negative 7 halves, x equals 1. And then over here, we might just say that the zeros are, right? So when is it 0? At x plus 3. And so x equals negative 3 is our 0. However, that's kind of a problem because the one thing we haven't done is we haven't analyzed the domain, and we didn't do that on the previous questions either. So that could have led to an error. So now let's think about the domain before we answer this question. The domain, you again ask yourself, what can't I do? Well, I can't divide by 0. So to find the domain, I need to ask myself, when is the bottom 0? Right? So on these zeros questions, it has, kind of summarized down to when does the numerator equal 0? Because that's where the math takes us. For the domain, the question is, when does the denominator equal 0? Because those numbers are a problem. And that's because of the way the math works. So I just need to ask myself real quick, and this factors So I know I can't use 3 and I can't use negative 3. So I would not call this a 0 because I'm not even allowed to use that point. So we will talk about the implications of that a little bit later. But we would not say that it has a 0 here. No zeros. All right. This video has turned out quite a bit longer than I was expecting. Got a lot more questions here. As I just discussed, finding the domain of the function comes down to figuring out when the denominator equals 0. So I know that this factors into 2 over x plus 2, x minus 2. And so what it comes down to is figuring out when the denominator is 0. So the denominator cannot be 2 or negative 2. So the domain is going to be negative infinity to negative 2, not including negative 2. Also, between negative 2 and 2 is fine. Also, greater than 2 is fine. In other words, we have vertical asymptotes at negative 2 and positive 2. And then we come over to this one. And again, if you want to figure out what the domain is, we just have to ask ourselves the question, when does the denominator equal 0? And let's see, that's going to factor into x plus 4 and x plus 2. And so we know that x cannot equal negative 4. X cannot equal negative 2. And so writing this out as a domain, we would say the domain, again, everything but those two numbers, which means we're going to use everything from negative infinity to negative 4, not including either one. We're going to pick it up at negative 4 and go all the way to negative 2. And then we're going to pick it up at negative 2 and go to infinity. And here, same issue. We've got the denominator cannot equal 0. And that's going to happen when x is 3 and x is negative 3. So x cannot be 3. X cannot be negative 3. So the domain is everything but 3 or negative 3. All right. So up here, I said explain how you can summarize how to find the zeros of a rational function, and I've talked about that. That's whenever the numerator is 0. How can you summarize the domain? That's when everything except for when the denominator equals 0. Now, I don't want you to memorize. I want you to think. None of these things are difficult to consider if you understand the questions that are being asked. It's more important to understand what's being asked when and asked about the domain rather than trying to memorize, oh, I do this thing. Think about the number sense. Don't think about memorizing. Okay, there's probably no way I get all this done in one lesson, but let's finish this video anyway, even though I might break this up in class. Put everything you know together and sketch a graph. Label the intercepts and the asymptotes. Before I do anything, I want to consider the factored version of all of these. So this factors into x plus 2 and x minus 2. Okay, so let's think about the zeros. And I ask myself, when is the numerator 0? And it is never 0. So I have no zeros, I have no x-intercepts. If I think about the domain, I know the denominator cannot be 0. So the domain is everything except for x equals -2. X cannot equal +2. So I'm kind of just cheating on how I write the domain right now. Because what does that tell us? That tells me that's where my vertical asymptotes are. And that's what I really care about. So my vertical asymptotes are filling in those gaps. So they're going to be at x equals 2 and at x equals -2. So I've got my zeros. I've got my vertical asymptote. The only thing I really need probably left is my horizontal asymptote. And that's where I think about the end behavior. As x goes to infinity, what happens? Well, my degree on the bottom is bigger. And so we have a horizontal asymptote at y equals 0. Let's put what I have down and see if that's enough. All right, I have vertical asymptotes at x equals 2, x equals -2. I have a horizontal asymptote. I'm going to do this in red here so it stands out. At y equals 0. I have no zeros, so I have really no points to put on this graph, other than I did not do the other last easy point to find, and that would be I should have found the y-intercept. So let's squeeze in the y-intercept, and that's when x equals 0. When x equals 0, I get -1/2, 2 over -4. So I've got the point 0, -1/2. Okay. All right. We know what happens at asymptotes. We know that I'm approaching 0. So I know I'm approaching 0 from below or from above. So I don't know which one. I know here I'm coming in and I'm approaching 0 from above or below. I also know that I approach a vertical asymptote. I'm either going up or I'm going down. On the other side, I'm either going up or I'm going down. Here, I'm either going down or I'm going up. So there are all kinds of options of what could be happening here. The only place that I am solidly confident in is in this section between the two vertical asymptotes. Because keep in mind, having and knowing where points are is very powerful, but also not having points is also powerful. What I mean by that is we have no zeros here, right? There's no zeros in between here. So knowing this point and knowing as I approach the asymptote, the vertical asymptote, I have to either go up or go down. Well, since I cannot cross and have a 0, that tells me for sure that this graph is going to look something like this. Now, unfortunately, I don't have any more points, so I don't know whether I'm option, and I'm going to erase this, I don't know whether I'm option A or option B on this side. But it's easy to find out because all I need to do, because I know there are no zeros, so if I plug in any number bigger than this vertical asymptote, which is at 2, if I plug in anything bigger than 2, if it's positive, then I know it has to be this. If I plug in a number bigger than 2 and it's negative, I know it has to be this. I don't even care what the number answer is. I just want to know if it's bigger or smaller than 0, if it's positive or negative. So I'm going to simply do an analysis that I'm going to do a lot of. I'm going to go to the factored version, I think, is the where to do this. Oh, my clicker's working. And I'm going to plug in a very large positive number. It could be a billion, it could be 10. It doesn't really matter, whatever's easiest to do the math on. So when I plug in a number that's bigger than 2, like say 10, I get on top a positive number. On the bottom, I get positive. 2 plus 10 is positive. and 10 minus 2 is positive. So I get positive divided by positive is positive. So I know with no doubt or hesitation that my graph looks like this. Now I'm going to plug in something on the other side of negative 2, like negative 100, negative a billion. It doesn't matter, something very negative. My top is 2. Negative a billion plus 2 is going to be a negative number. Negative a billion minus 2 is going to be a negative number. A negative times a negative is a positive. So I have a positive divided by a positive, and that tells me my answer is positive. So that is what it takes to kind of graph this problem. Let's go ahead and analyze this one. I think let's do the stuff I can tell right now. I can tell right now if I plug in 0, then my y-intercept is going to be 0, negative 7/8. My horizontal asymptote is going to be, the degrees are the same, and so we go to the coefficients, and it's going to be y equals 2. Everything else is going to be easier to answer factored. So now let's factor f of x. The denominator is x, and 4, and 2, and plus, and plus. The top, we've already done this one. It's going to be 2x, and 7, and 1, and positive, and negative. So what are the vertical asymptotes? And that's going to be when x plus 4 cannot equal 0, and x plus 2 when that equals 0. So at x equals negative 4 is one of my asymptotes. X equals negative 2 is my other asymptote. And what are my zeros? That's going to be when the numerator is 0. So 2x plus 7 could equal 0. X minus 1 equals 0. X equals negative 7/2. X equals 1. All right. I have my horizontal asymptote. I have my vertical asymptotes. I have my zeros. I have a y-intercept. Let's see if that's enough. And I'm just going to make a command decision. We're going to do this another day. Vertical asymptotes, negative 4. Label it. Negative 2. I should have spread it out more. You know what? I'm going to move my axis over. Come on, pencil. Are we back? There, we're back. All right, so there's my y-axis. Okay, and then negative 2, we'll say is right here. Okay, did those. Horizontal asymptote, it's going to be at positive 2. Label it. And what else? Vertical, horizontal, zeros. Negative 7/2 is negative what? 3.5. So that's going to be in here someplace. Negative 7/2, 0, and 1, 0. Okay, I think we're going to be in pretty good shape graphing this one. We might need to do a little bit of investigation. Oh, there's one more thing I haven't done, but I barely need it. But since we know it, let's use it. I've got the point 0, negative 7/8. All right, knowing what I know, I have a 0 here. I have an intercept here. I have to approach this horizontal asymptote. I have to approach this vertical asymptote. There's only one way that could possibly happen, and that would be with a graph that looks roughly like that. Okay, let's go to the very far side of the graph. We'll skip the middle for a moment. Now, we don't have any points out there, but that's good news because the absence of points here tells us exactly what the answer is. There's no way for me to approach this asymptote going down and this asymptote going to the left without crossing through and having a zero. I can't get from the bottom to the top without having a zero. So the absence of a zero tells me that the answer has to be up here. Okay, but the middle is still a little bit unknown to me. I could be going up on this side and down, or I could be doing the opposite and passing through the zero, right? So I could be coming in and doing this, or I could be coming down and doing this. And I don't know which one it is. So what I need to do is just do some quick investigations. So to keep track of it, I'm going to write the following. This is at -2. So I'm going to say, as x approaches -2 from the left side. So I'm going to put a negative here. So that says, as x approaches -2 from the negative side or from the left. Then what the heck is y doing? So what am I going to do? I'm going to pick a number that matches that. I'm going to go so close to the asymptote that if it's positive, I know I'm going up, and if it's negative, I know I'm going down. So I'm going to plug in just to the left would be -2.00001. Okay, and I'm going to do that analysis right here. I just need to know if it's positive or negative. So it's getting kind of messy. My apologies. I'll try to organize this a little better in class. Okay, so when I do this analysis on top, a -2.00001 times 2 is -4-ish plus 7. That's going to be a positive. So I get a positive. -2 something minus 1 is going to be a negative. So on top, I have a positive times a negative, which is a negative. -2.00001 and 4 is a positive. -2.0001 and a positive 2 makes a negative. So that makes a negative. And a negative divided by a negative is a positive. So with that information, I feel very confident that I'm coming down and I am going to continue going down. Now, it is possible that I bounce here instead, right? That's a possibility. But I don't think that's what happens. But if I want to find out, then I can ask the question. By the way, this would be y goes to infinity. And so if I want to ask the question on the other end, as x goes to 4, -4, from the right side, so from the positive side, then what happens to y? So a number like -3.99999. So let's go back to my factored version and let's plug it in. Negative something slightly less than 4, -3.9999, is going to be a number very close to -8. So that's going to be -8-ish plus 7. That's going to be a negative. And negative minus 1, that's going to be a negative. So on top, I have a negative times a negative. On the bottom, I'm plugging in -3.9999, which gives me a positive on that factor. And that's going to be a negative. So I get a positive divided by a negative, which of course is a negative. So that tells me I'm definitely going down here. All right, that seems like a lot, but once you get good at it, it's something that really only takes about a minute and a half to do for the whole thing. All right, we're going to stop there, and we will continue talking about this over the next several days and over the next several videos.